Okay, thank you so much. Hi, everyone. My name is Caeley Pittman, and I'm a fifth-year PhD student at Boston University working with Professor Catherine Espaillat. Today, I'll be presenting my work from the past few years on the HST Ulysses sample. At the last Cool Stars meeting, I presented my first paper on this sample. It was on the first 9 stars studied, but now I'm presenting the essentially final results from the entire Ulysses sample. So classical T-Tauri stars are well known for having complex outer disks of gas and dust, as you can see in these ALMA D-sharp images. But if you zoom in, you also see very complex inner disk systems, as we've already seen today. So I don't need to go too deeply into the system, but basically what I'm focusing on is the central T-Tauri star that's truncating the inner gas disk, causing material to flow along the magnetic field lines and crash onto the stellar surface, producing an accretion shock. And as Benoit pointed out this morning, this is a very efficient process. So most of the energy that is coming in from this potential energy infalling is converted into radiation that we can observe. So looking at continuum excess emission in the ultraviolet and optical from accretion is a really good way to actually characterize the accretion process. So previous near ultraviolet surveys were limited to the closest and brightest stars. This is because T-Tauri stars are already very faint and they are in dusty star forming regions, so you have to deal with a lot of attenuation as well. But the Ulysses program worked to kind of remedy this limitation. So Ulysses is a director's discretionary time program that dedicated 500 Hubble orbits to observing about 60 new T-Tauri stars. And it observed in the far ultraviolet all the way through the near infrared, so from around 0.13 microns to 1 micron. And it was across the range in T-Tauri ages, so from young to old regions. And then we have the Odysseus collaboration, whose PIs are Catherine Espaillat and Gregory Herczeg. This is a group of over 100 international T-Tauri star experts who are working to maximize the impact of the Ulysses dataset, both through getting contemporaneous observations and X-ray, optical, both ground and space-based, and actually doing analysis. So if you go to the Odysseus webpage, we have a list of our growing list of publications, you can see there, and you can reach out if you are interested in joining. And then Penelope is a large program on the VLT led by PI Carlo Minara. This program obtained contemporaneous high and medium resolution optical spectra, and this allows us to obtain consistently derived stellar parameters for the entire sample. So instead of just doing a literature search and getting parameters that were derived in all manner of different ways, they're all derived in the exact same way, and that gives you a really strong starting point. And the Odysseus website also lists their growing list of publications. So let's look at a classical T-Tauri star spectrum from Ulysses. This is SY Cha. It's a K7 T-Tauri star. And this is its observation in the near ultraviolet through near infrared from Ulysses. And to put it in context, let's add a non-accreting T-Tauri star. This is scaled to contemporaneously measured veiling. So we trust the scaling of the weak-line T-Tauri star, the non-accreting T-Tauri star. And you can see that there is a clear continuum excess from the ultraviolet all the way through to the end, to this near infrared region. And this can be attributed to an accretion shock. So the accretion shock model we use is from Calvet and Goldring 1998, and it's been most recently implemented by Professor Connor Robinson, myself, and Dr. John Windeborn, all of us working with Professor Espaillat. And this is what it looks like. So if you zoom in just to this point right where that accretion flow is crashing onto the surface, it's approximated as a one-dimensional flow. It crashes on the surface, creates a strong shock that emits X-rays. Those are quickly thermalized, and we ultimately observe them as ultraviolet and optical radiation. So now I'm going to show you how I actually applied this model to the Ulysses dataset specifically. We start with a non-accreting T-Tauri star, the same spectral type as your science target. So this is just that gray spectrum I showed before. And then we add a hotspot. So this is the hotspot that's produced by this accretion flow. And we know both from 3D magnetohydrodynamic models as well as observations that these are not isothermal. They're not they have structure. They have density gradients. So that's represented by these different colors in the hotspot. And the accretion flow that would cause a hotspot like this looks something like this, where it has its own density gradient. It has some accretion rate, m dot, and it has an energy flux density, which is this cursive F. Now, this continuous function is both computationally challenging and would come with a lot of degeneracies to model this. We find that it's totally sufficient to use 3 discrete accretion flows with each having their own energy flux density, this F. So we have the F low, F medium, and F high columns, each with their own associated filling factors, these lowercase f's. And this is what we together call our multi-column magnetospheric shock model. So we can calculate accretion shock spectra using the consistently derived stellar parameters from Penelope. And the low F column spectrum is here in cyan. And you can see that the peak of its emission is in the near infrared. It's around 0.9 microns. Whereas the higher energy column here in brown, its peak is in the ultraviolet. So they have pretty distinctly different spectra depending on the energy flux densities. And I want to emphasize that this whole region is inaccessible from the ground. My plotting does automatically kind of emphasize this region. But if you want to characterize the highest energy region of the accretion spectrum, you need to observe from space. So now I'll show how we actually apply this to a T-Tauri star spectrum. So now we're back to SY CHA. This model fitting is actually done in an MCMC manner. The parameters, we have 4 free parameters fit simultaneously, but I'm going to show them one by one for clarity. So we fit for the extinction, so how much interstellar reddening there is. We add in our photospheric template. And then we can start adding in the accretion column spectra. So here's the low F column. In this target, its best fit is covering 23% of the stellar surface. And if we add these two together, the non-accreting template and the low energy density column, you can see we've taken care of a lot of that optical excess emission, but it's still missing in the ultraviolet. So we can add in the medium F column, in this case covers 1% of the stellar surface, and then the high F column covers 0.01% of the stellar surface. And add it all together and you get your continuum fit. So we are able to effectively explain the continuum excesses using this accretion shock model. And again, much of this excess is only observable from space. So in some cases, it's only about 4% of the accretion luminosity that's at these short wavelengths. But for some high accretors, it's up to a quarter of the total accretion luminosity that's at these short wavelengths that you can't observe from the ground. So now I'll show the results from modeling the entire Ulysses sample. It's about 70 T-Tauri stars. It's both the new observations as well as consistently processed archival data. We see that accretion rates span approximately 3 orders of magnitude, where the higher mass K-type stars tend towards higher accretion rates and the lower mass M-type stars tend towards lower accretion rates. And this is expected. There's a well-known relationship between stellar mass and accretion rate. And the distribution appears bimodal, but I think we don't really have a physical reason to expect this. I think this is more of a selection effect because the initial Hubble observations were bright stars. Those were over here. Ulysses specifically wanted to extend this down to dimmer stars, so added a lot over here. We find that the hotspot surface coverage is typically under 10%. And when the surface coverage is higher, it tends to be from the lowest energy emission. When you look at the highest energy emission from the high F column, there's always small surface coverage, so it's never covering more than 5% of the stellar surface. And these results agree with 3D MHD models. So this is a model from Professor Jiawan Zhu. So this is just showing a hotspot that is from a 3D MHD model. And here, I just want to focus on the blue curve This is a cumulative distribution of the surface coverage of the accretion hotspot. And I specifically want to focus on these two shaded regions. So the colors are different, but in this case, the red is the higher energy emission, and blue is, or green is lower energy emission. And we see, if you go from the surface coverage over here, you can see that the high energy emission has low surface coverage, so it's definitely less than 5%. And the lower energy emission here, it's around 10%. So this is in agreement with what we've found. We also see that the filling factor, the surface coverage, is potentially correlated with the stellar mass. So it's a correlation coefficient of about 0.6. And this even includes the one brown dwarf in our sample. I know there are a lot of brown dwarf people here. We've got one covered for you. And it does seem to kind of follow this trend as well. So now our two big takeaways. First, we observe diverse accretion column structures, so we don't see the same thing in all 70 stars. So there's no one column, high, medium, or low, that always dominates the accretion flow. This is showing all of the sample in order of accretion rate, with accretion rate on the y-axis. And the colors are showing where the accretion rate is coming from, which column, high, medium, or low. So there are cases where it's almost all the low energy emission, almost all medium, almost all high. You see lots of different structures where you have all three or just two. So there's no one kind of structure that we see across the sample. Here's our brown dwarf again. It's the lowest accretor in the sample. Here's an example of a low F-dominated spectrum. So the blue is the highest, a medium F-dominated, so the green is the highest, and a high F-dominated, so the brown is the highest contributor. And then the second big takeaway is that accretion column structures are often poorly constrained by ground-based spectra. So I did this test where I ignored all of the data at the short wavelengths and only fit what's observable from the ground. And often the model, even though it'll fit at the visible wavelengths, it does not continue into the ultraviolet. So even though you might seem to have a good fit, it might not actually describe reality. And it's not always in one direction. Sometimes it's too high, sometimes the model's too low. So that's something we intend to try to find some correlations between ground-based observables and what we see from the space-based observations. So that'll leave my summary. Thank you for your time, and I'm happy to take questions.
Thank you, and we have time for one or two questions. Yeah.
I wonder if you comment on the energy flow, not just the mass accretion rate. And the reason I ask is you've not mentioned the X-ray emission, which may be important. And also Lyman alpha, which drives the H2 emission in the far UV. So, please.
Can you repeat the question, please?
Okay. I'm not sure if I can. Okay, so you want comments on just the energy balance?
Yeah.
Okay. So I focus on what we observe from the hotspot, and that is mostly in the ultraviolet and optical wavelength ranges. So I'm not personally familiar with the X-ray emission, but this definitely is a high energy process. I know Kevin France looks at the Lyman alpha from all of these targets. And we are looking for correlations actually between the energy distributions of the hotspots and the inner disk H2 emission. So we do see correlations between higher energy emission makes brighter H2 in the inner disk. Yeah, sounds good.
One more question. And the next speaker come up.
Jamie Tyler, University of Florida. You showed us a very diverse set of accretion column structures. And I was wondering if there's anything that correlates with what you're seeing. Is there any way of guessing, or is every star just special?
Yeah, so that's something we had this idea to make this plot about a week ago. So I haven't gotten a chance to dive really deep. I'm sure there will be, like, the most expected correlations are that we'll have this higher energy emission from higher mass, higher luminosity stars. I mean, that's justified even just from the brown dwarf here is dominated by the lowest energy emission. Beyond that, I need to look more into it, but planning to submit this paper in the next few months, so it'll be in there. Thanks.
Let's thank, Caeley again. And the next speaker will be Mary Deferode, talking about mass dependence of convective envelope overshooting.